This is question number 5 from the SACE Stage 2 Physics course companion from Subtopic 2.2, Motion of Charged Particles in Electric Fields. This is a fairly difficult question. Here we have an electron entering halfway between two parallel plates which have some potential difference over the plates. We're told that separation between the plates is 5 centimeters and that the electron travels 3 centimeters before it strikes the positive plate. What we need to do is determine the potential difference delta V. So here, unlike all the other ones, we need to work backwards using all of our expressions that we've been using so far to try and work out the potential difference. So just to think it through how we're actually going to work this out, the only way we can really determine the potential difference is using our expression for the electric field, delta V over D. Unfortunately, we don't have the electric field in the question just yet, but we need to work that out. In order to work that out, we need to calculate the acceleration of the electron to work out using information that we're given. From there we can work out the electric field. Once we have the electric field, we can determine the potential difference. But how are we going to work out the acceleration? So in order to work out the acceleration, we're using our constant acceleration formulas. So here we don't really have much except for the initial horizontal speed and the distance traveled, but we can use that horizontal distance and the horizontal speed to work out the time, and then from there we can work backwards using the constant acceleration formulas to find A, then E, then delta V. So let's begin by working out time, so just to make sure what we're doing, so we can work out this time, work out the acceleration, to work out the electric field, to work out the potential difference. So let's begin. So we have D equals VT, therefore the time will be distance traveled over velocity. Now here we're considering the horizontal components of the motion of the electron. So here the distance traveled is 3 centimeters, and the speed of the electron is 2.5 times 10 to the power of 7. If we substitute that into our calculator, we get 1.2 times 10 to the power of minus 9 seconds. So now we have the time. We can use our constant acceleration formulas to work out the acceleration. So here we have V0 VATS. So V0 is 0 because the initial vertical velocity is 0. We don't know V. We're trying to work out the acceleration. The time is 1.2 times 10 to the power of minus 9 seconds. And the distance traveled, the vertical distance traveled is 2.5 centimeters because it enters halfway between the two plates. So here this will be 2.5 times 10 to the power of minus 2. So looking at this, V0 AT and S, we'll be using S equals V0 T plus half AT squared. Conveniently, V0 is 0, so our expression just becomes half AT squared. Therefore, the acceleration will just be 2s on t squared, which we can substitute our values in. So 2 times 2.5 centimeters time 1.2 times 10 to the power of minus 9 seconds squared, which if we substitute into our calculator, we get 3.47 times 10 to the power of 16 meters per second squared. So now we have the acceleration. We can determine the electric field. So E will be just, I'll work backwards. I'll do the initial formula first. So we have A equals BQ on M. So rearranging this will be MA over Q, which we know the mass of an electron is 9.11 times 10 to the power of minus 31 kilograms. Acceleration we've just calculated. And the charge of an electron is just 1.6 times 10 to the power of minus 19, which we substitute into our calculator to get 1.98 times 10 to the power of 5 volts per meter. Finally, we can work out the potential difference that we have. E is delta V over D, therefore delta V will be E multiplied by D. We've just calculated the electric field, so 1.98 times 10 to the power of 5. Separation of the plates is 5 centimeters. 5 times 10 to the power of minus 2, which if we substitute into our calculator we get 9.878 volts. That's way too many significant figures, so we'll just write this as 9.9 times 10 to the power of 3 volts. And there we have it. So that was a fairly challenging question. Lots of small parts, like none of the individual steps themselves are very difficult, but tying it all together is fairly challenging. The easiest way to do these sorts of problems is to work backwards like I did. So starting off with electric fields, delta V over D. Okay, we need to work out the electric field. How can we do that? Calculate the acceleration. How do we calculate that? We need the time, and then everything else falls into place. Oh yeah, there you are. I hope you enjoyed that question. It was a good, challenging one, and yeah, quite good.